Well, welcome back. This is DC electronics topic number 7. We're going to be talking about troubleshooting circuits as well as the challenge question solutions from topics 5 and 6 YouTube videos. Now, this sequence of training videos is intended for you to be able to self-study at home or to supplement your lessons in a electronics or engineering or electronics technology program. So, without further ado, let's jump into topic number 7, which is to look at the troubleshooting questions and challenge questions that were previously presented in topic number 5 and 6 videos. Specifically, here is the question that was posed in topic number 5. And that was a voltage divider analysis question. So with the voltage divider, you were shown, you were given a 220 ohm resistor, 300 ohm, 330 ohm resistor, and a 220 ohm resistor in sequence as R1, 2, and 3, as shown in the illustration. And with voltmeters attached at voltmeter number 1, voltmeter number 2, voltmeter number 3, you needed to determine several things. The sequence of calculations is shown as presented, and we'll go over these calculations in a moment. What would be helpful to all of us is probably to go back a moment to topic number 5 and look at the example that I gave you that will help solve this particular challenge question. The slide that will best help you review how to solve the challenge is taking a look at this slide from previous topic number 5, and it is an explanation on how to apply the voltage divider formula. We abbreviate that as VDF for voltage divider formula. And if you look at the formula on the upper right-hand part of your screen, you will see that VRX is a voltage calculation for some kind of voltage across a resistor. Which resistor? There happens to be 3 of them. And the formula shows Rx. So X is the number of the resistor of interest. And then in the formula, it shows VRX, the voltage across this particular resistor, any one of these 3, is equal to a fraction, a proportion, a part of the total voltage. Your VS, your voltage source, is your total voltage. So how do we apply this? Well, the first thing we need to do is to look at all 3 resistors, and they are given as 330 ohms, 100 ohms, and 220 ohms in that sequence. And so we will add them up to find a total resistance. Total resistance is calculated as the sum of 3 resistors. So we would have calculated 330 plus 100 plus 220 will calculate to be 650 ohms. Now, to calculate the voltage across R1, we could use Ohm's law, but I wanted to show you what some people consider a quicker way of doing this without needing to calculate current for Ohm's law. One way to do this very quickly is with voltage divider formula. So let's go ahead and apply voltage divider formula for resistor number 1. And so the formula goes to show on the right-hand side, VR1 equals a fraction of R1 over R total, close parentheses, times your voltage total. And if we look at the numbers, VR1 would be equal to the voltage across the first resistor is equal to 330 ohms divided by the total of 650 ohms, then multiply by 5 volts, and we calculate 2.54 volts. Using the same method, we would calculate VR2 as 769.23 millivolts and VR3 as 1.69 volts. And the total current is calculated using Ohm's law as 5 volts divided by the 650 ohms, and that will calculate to be 7.69 milliamps. So these are the numbers of interest, not hard to calculate. We'll show you a review of that on how to do this with our calculator. Just as a quick aside, let's go ahead and verify these numbers that we've previously or hopefully just now calculated. And if you haven't taken the time to calculate this, freeze the screen. Freeze the screen and do these calculations on your calculator to make sure you feel confident in being able to make these calculations and come up with numbers that are similar to what it is that we have on our display screen. So let's go ahead and give that a pause. let you do your calculations, and I will then go to the calculator and work this out with you together. And actually, before jumping into the calculations, I've mentioned a number of times in previous training videos that you should be writing down in chronological order. I can't speak, I'm dyslexic. Sorry. Anyway, you should be putting down these formulas and these calculations in your journal. So if you haven't already done so, please take these numbers down. And then you'll have them on the side as we go through the calculations with the demonstration of the calculator, and then the keystrokes on the calculator will make sense. If you've been following the directives that I've been giving all along, then this should already be in your journal back for topic number 5. So let's go ahead and jump into the calculator exercises once you have copied these numbers down in your journal. All right, so with the numbers that are in your journal, first thing we want to do is to calculate total resistance. And doesn't matter which calculator I use, but let's just go ahead and use this one for now. So we have 330 plus 100 plus 220, and you want to confirm that you get 650. Now this one's showing you scientific notation. Press engineering, and engineering shows you 650 with no particular power of 10. So this is 650 whole ohms. Now, after you calculate total resistance, we're going to apply voltage divider formula. And voltage divider formula is your first resistor of 330 ohms divide by the total resistance of 650 ohms. So algebraically, your calculator would do this left to right first, so you don't have to put this in parentheses. The calculator has the smarts to do things from left to right. As we do the division first, we don't have to hit equals and then multiply. We just simply go to the next math function, which is multiply by 5. And we hope to see on our calculator something that looks like 2.54 volts. Boom. And you would round this off to the second digit after the decimal point as 2.54 volts. And so the next calculation for R2 would be the ohms of R2, which is 100. You're going to divide that by 650 and multiply by 5. We should get something that's close to 769.23 millivolts. And, well, the calculator threw it into scientific notation, which is useless to us. We're going to hit the engineering key. Bam, there it is, 769.23, 10 power negative 3. You should know by now that 10 power negative 3 is, in fact, milli. If you're not sure, we can go to this handy-dandy calculator, which does all the metric prefixes for us. And so we will go ahead and take 100 and divide by 650 and times 5, hit equals, and lo and behold, it automatically gives us the milli prefix in the corner. 769.23 millivolts is the voltage that we would calculate for VR2. So one calculator shows this as 10 minus 3, which is equivalent to, which is the power of 10 for milli. This calculator does show you the actual engineering prefix with a lowercase m. All right, let's do the last one. And the last one is 220. So clear. So 220 divide by 650 times 5. Boom. And that works out to be 1.69 volts. So using your voltage divider formula, this is how you verify your measurements. And if we go to check our measurements, we could do that very easily by doing this, move this out of the way. Here's your 3 resistors. And as I've said before, in your circuit building process, I'm going to yank out this jumper just for a moment and put in the LED. The LED is nice to show us that, yes, the circuit is lit. We have current flowing through. It is built properly. We'll take the LED out. When the LED is out, you can measure the resistances individually to confirm what it is that we have. So we put the jumper back in, and turn off the power supply, and I can actually, for me, I remove the power supply. You don't have to if you disconnect one of these jumpers. So for example, I'll just leave the jumper on, for example, leave the power supply on, remove the jumper, just set it aside, and let's just go ahead and very quickly double check our ohms for this. And I will go ahead and do this. Okay, and as I said, as a reminder from some of our first videos, to make sure your multimeter is working properly, we want to go to the continuity test mode, which is this position, shows a little sound symbol. Touch the two prongs together. We should see this change to almost 0 ohms. And if the microphone picks this up, you might even hear a beep. So it lights up, it goes to almost 0 ohms, like so. You may or may not hear the beep, but the green light says we've got continuity, or we're pretty close to 0 ohms. So the first thing you want to do is make sure your leads are working, multimeter is working properly. And now let's go ahead and set to ohms. So the omega symbol is right here. So we want to make sure that the resistors are in the right position. So we go ahead and touch here to here, and hope to see something close to 330. We see 332.3, and the next one here, we touch here to here, and we should see something close to 100, which we do, 101, and we touch here to here, and we see something close to 220. It's at 219.9. Wonderful. And does it make any difference if we go red lead on the other side, black lead on the other side? No, it does not. This is a reminder that your resistors are not polarized. So when you're measuring resistance, the polarity of the leads, your probes, doesn't make any difference whether you hook red to one side or red to the other side, black on either side, okay? Okay, now if we want to measure total resistance, here's something that's interesting that I said that would be a problem, and that is if I put the jumper back in place of the LED, was, let me just go ahead and pop this right back here so you can see, yes, light it up. It's on, circuit flows, current. This is wonderful. Put the LED out, and let's go ahead and grab this little jumper, put it back in, like so. And if you go to measure total resistance now, we're not going to measure the 650 ohms. Why? Look at that. It's like 533 ohms at 0.534 with the kilo. You see the kilo on the display of the digital multimeter, saying, hey, what gives? What's wrong with this? Well, I said before, you cannot measure total resistance on the board if your power supply is on the board. When you say, well, wait a minute, the power supply is off. I don't have any current flowing through. I'm going to turn it on. You turn it on, and then for sure, you're not going to get any ohms because resistance cannot be measured while electricity is flowing. So you figure, okay, I'll turn it off, and therefore, if it's not on, it should not affect my total resistance. And yes, it does, because there's circuitry in your power supply, and that power supply being hooked up on the positive rail and the negative rail, guess what, friends? It's going to mess up your total ohms. We are nowhere near the total ohms that we expect to be at 650. We're 534. So what do? If we want to leave this intact to measure total ohms, we do for a moment pull this guy off. Now it's off the board. And now if you go to hook this up here to here, ta-da, we'll get something close to our 650. And there's your 0.649 kilo. And so as another reminder, if you have a 0.649 kilo, how is 0.649 kilo 650 ohms or close to 650 ohms? Well, my friends, again, this is a review to a previous video, having to learn and understand how your calculator works and how engineering notation works. And very simply, let me just go ahead and show you this. Let's see, our reading was 0.649. Okay. Or what it is we can do, since I'm using two hands, I can put the two hands into one, kind of like so. I'm trying my best to do this without blocking the camera. Maybe I'll do it this way. All right. So 0.649, and I'm holding this with the right hand. And so with the left hand, I can just press hold, the little H, and it'll hold the display. Now I can take my probes off, and I can verify this number separately. So what I'm going to do is grab the handy dandy calculator. And show you with this style of calculator what we're going to do to calculate the 0.649 kilo as being 650 ohms. So if I key this in 0.649, and kilo is 10 power of 3, if you recall from our previous discussions. So here's my 10 power key. I'm going to hit the 10 power key, which gives me a 10 power and 3. So now I've keyed in 0.649 kilo. This display is now keyed into the calculator. If I hit equals right now, again, 0.649, 10 exponent 3 is kilo. If I hit the equal key now, boom, I will get scientific notation, which is useless to me, but I have an engineering button, hit engineering. Lo and behold, 649, no power of 10, so that's a whole 649 ohms, which is pretty darn close to our calculated 650 ohms. On the other calculator, which I've recommended for you, it can be done this way, and that is, we will go ahead, turn the puppy on, and then point. So there's my decimal point, 649. So there's my 0.649. And how I enter kilo on this calculator is I actually have a kilo button. So I hit shift. Here's my kilo button, which is right above the 6. Boom. And now you'll see on the display, I've got 0.649 with the K on the display, as opposed to the 10 power of 3 on display. And if I hit equals right now, boom, it automatically doesn't go to scientific notation. It goes right to the appropriate engineering value of 649. And we get 649 on both calculators, whichever way you do. All right, now once we verified the ohms, the next thing you want to do is verify the voltage. So we calculated the voltages. So let me bring the puppy back in here. And hopefully you've taken the time to double check your calculations. And let's go ahead, hook the power supply back on. And we were supposed to have something close to 2.54 volts. Okay, set this here back to DC volts. It says DC voltage. And let's go ahead and put our probes across. I'll turn this guy on, might be helpful. There we go. Now it's on. My jumper is back in place of the LED. Presumably current's flowing. Presumably I have voltage across each of these resistors. Each of these is dividing that total of 5 volts into parts of the circuit. So here we expected something close to 2.54. Measure, put the probes into one hand, and with the other hand, hold steady, hold steady. It'll jump around a little bit, but as steady as you can get. Press the hold key. Hold steady, hold steady, hold steady. Okay, are we close to the 2.54, 2.45? Not bad. Now let's go ahead, unhold, and let's do the second one. Second one, we expected 769 millivolts. Let's see what happens here. Put this probe on here. Put this probe on here. Hold with one hand. Press hold. I expected something close to 769 millivolts. You can see I've removed the probes. I've used the hold button in order to hold the display because the display does jump around quite a bit. And so what you do is press the button to hold, jot this number down, and compare this to your calculated value of 769 millivolts. So you go, wait a minute, I don't see milli on here. I see 0.761 volts. How is that millivolts? Well, again, we go back to our calculators. Go back to our calculators and let's clear and let's do a 0.761, 0.761 right there. And I'm going to hit enter, and on this calculator, it'll automatically go to proper engineering notation, which means we have 761, and it does show you the little m 4 milli. So it's pretty darn close to our calculated 769 millivolts. Our measurement 761 millivolts, as you recall, because the resistors have tolerance. I have ohms that are scattered in the breadboard itself, and there's a tiny bit of ohms on the wire leads and tiny bit of ohms on the jumper wires. We're not ever going to be exact, but this is pretty darn close and certainly close enough. On the other calculator, let's go ahead and pop this on here, and let's do clear point 761. So there's my decimal point 761. Hit enter, and I get some scientific notation, which is useless. What do I do? Hit the engineering key, ENG, boom. And with ENG, you can see 761, 10 power negative 3. You look that up on your engineering chart that you should have recorded into your journal by now. 10 power negative 3 is milli. Just as it shows here on this calculator, we have milli. All right, last one is to verify that we have the 1.69 volts. So go ahead, pop this guy back, release my hold, get my probes back on. And I'll show you something interesting also. Check this out. We expect something like 1.69 volts, and you go to hook this up, you say, hey, that's not bad, 1.71, hold. But wait a minute. Something's odd about this. Do you see what's odd? Take a look at your, or different, maybe not odd, but what's different on your multimeter, you see this negative sign in front of your voltage? Say, oh my gosh, how do I get negative voltage? Well, I explained before, and if this happens to you, don't freak out. It's not a mistake. All that has happened is your probes are not on the correct polarity for measuring voltage. We said that the polarities don't make any difference for measuring resistance, but for measuring voltage, the polarities of the probes are very important. So the red probe is connected to the negative rail, and the black probe is connected to the positive side of the resistor. We have to flip this around. The red probe should be on the positive side of the resistor, and the black probe on the negative side of the resistor. If I release the hold, the negative will go, symbol will go away. Ta-da! And now we can hold, we can see that without the negative sign, we are measuring a positive 1.718 volts. So this is just a word to the wise, and I'll do one more, and that is very often, because we're in a haste to get things done, we might measure our total voltage this way, and we hope to get something close to 5 volts, and we're measuring, from one rail to the other across all 3 resistors. You press hold, you say, hey, I've got pretty close to my 5 volts, and then you realize, wait a minute, what's this negative sign? It's not, you have not done anything wrong. There's nothing wrong with negative voltage. All that tells you is to be mindful of what color probe needs to go on what part of your circuit. So the red colored probe needs to be on the more positive side of the circuit. The black colored probe needs to be on the more negative side of the circuit. I'm going to hold this in place with one hand, and with the other hand, release the hold, and the negative sign will go away. Ta-da! Negative sign went away. It's measuring 5.11 volts. Okay, and the reason why it changed from 5.12 to 5.11, I'm holding this with one hand, and I might have a little micro jitteriness in my hands, and so maybe I'm not pushing down hard enough. I never want to be pushing down hard enough to break my probe leads, but I've got a nice firm connection here. Let go, hold firm with both hands, like so, with one hand, and see, now I'm pressing down just a tiny bit harder. Press hold. I got a 5.13. So don't sweat the little micro numbers, the 100th of a decimal place for voltages. Are we close to the board's output of 5 volts? Yeah, we're pretty close, and we're happy with this because this board happens to put out a little bit more than 5 volts. Now, some of these boards will put out the voltage like mine at 5.13. If yours puts out a voltage at 5.02, great. If yours puts out a voltage at 4.97, that's okay also. There's a margin of error. As long as it's close to 5 volts, we are dancing the happy dance. Okay. Okay. So we've now verified these. Now let's go back to the slides with a new challenge. And the challenge is to calculate the exercise with a different resistor in place. Okay, so we're back to our slides. So here was the challenge. We're changing our resistors slightly. We're changing our position of the resistor slightly. We're using one resistor that's different from before. You look in this circuit here, you can see there's no more 100 ohm resistor. I have as R1 220 ohms. I have as R2 330 ohms, and I have as R3 another 220 ohms. So the first thing you need to do is to, as you go to fill in this sequence of calculations to be done, what you ought to do, if you haven't done this before, is to copy this page down in your journal and leave spaces for voltages. Because you're going to calculate these quantities ahead of time and see if you can come up with a prediction of what these voltages ought to be. And then we're going to make sure we build it and do the measurements and see if we're on the right track. So go ahead and hit the pause button now and transfer these formulas and this information of this page on into your journal. And let's then proceed to start with some of these calculations. Let's go to here. Hold on. Okay, so before I start pushing buttons, you should be doing, before I do, as I've shown you before, your formulas for voltage divider formula should already be written in your journal. All the questions from the challenge analysis number 1 should also be written in your journal, and then we'll just simply fill in the blanks as we go along. So the very first calculation you're asked to do is V total. V total is voltage source, which in this case is 5. Nothing to calculate there. In the series circuit, that is your total. Now, the next thing you want to calculate is R total, and R total in series is the sum of each of the resistors. So you want to add, turn this guy on, 220 plus 330 plus 2, oops, messed up, sorry, 220. So we add these guys up, and this equals 770 ohms. Never hurts to double check, because sometimes your fingers are fat like mine are, and I might miss a button. And so just because you see a number on the calculator, it only takes a moment to recalculate. So 220 plus 330 plus 220, and just feel really confident that the calculation is consistent. And as long as it is, then you can write that value down. So the R total for this challenge analysis number 1 is 770 ohms. Previously, we had 650. Now we have 770 ohms. So the first task is to use voltage divider formula. And voltage divider formula, we're going to take R1, and so we're going to do it this way. Okay, so with this information in your journal, the formula for voltage divider formula, VRX, being the unknown resistor, is that particular resistor value divided by total. And in parentheses, this will be multiplied by voltage source, which is the same as your voltage total. So specifically, if we wanted the voltage across R1, then we use the ohms of R1 divided by total ohms times total voltage. So in this particular case, turn on your calculators. On button is there. And let's go ahead and do the calculation. We're going to start off with 220 ohms, so 220, and we're going to divide that by the total ohms, which in this case is 770 ohms. So 770, and then multiply this by the 5-volt source, and we should calculate a number. You should do this calculation. Don't wait for me to pop up the number for you so you can just copy it down. You should do this on your calculator. This is a hands-on drill. And who needs to learn this? Me or you? You. So who needs to do this? Me or you? Both of us. But you need to do this before I show you the answer. And so if you've done the sequence into your calculator, then go ahead, hit equals, and voila. You should have something that's close to 1.43 volts. Okay, so remember the 1.4285 we showed you in previous topic video how to properly round your answers so that we are consistently 2 digits after the decimal point, which places us at the 100th of the digit, so this would round to 1.43 volts. So you write down 1.43 volts for VR1. So you should also then clear the calculator. Let's go ahead and apply the same formula for VR2. So the only thing that changes in the formula is wherever we saw 1, we would replace that with an R2. So if we wanted the voltage across R2, we take the ohms of R2, which is 330, and divide by the total ohms, which is 770, and then multiply by 5, and we get 2.14 volts. Okay. And then the last calculation is VR3. So the value of R3 is another 220, and divide by 770, and then times 5, and we should have the same number we calculated a moment earlier, and this should be 1.43 volts. So those would be the voltages that you should be writing down for your VR1, VR2, VR3, and hopefully you've copied this sequence of calculations on your own scientific calculator and verify that we are on track with each other. Now, that being said, the next calculations are more interesting. The next calculations are for VM1, VM2, and VM3, meaning voltmeter number 1, voltmeter number 2, and voltmeter number 3. So let's just pause this for a moment. Okay, so as you look at this, you will see that VM1 is voltmeter number 1, and it's located on the far right of our schematic, and it shows a connection at the top of the circuit all the way down to the other end of the voltmeter to the bottom of the circuit. So voltmeter number 1 is measuring pretty much the same thing, exactly the same thing as voltmeter number 4. And take a look at this. Voltmeter number 4 is connected to the top, and voltmeter number 1 is connected to the top. Voltmeter number 1 at the bottom is connected to the ground, and voltmeter number 4 is connected to ground. And that should give us our flat 5 volts. So voltmeter number 1 is across all 3 resistors. And one of the things you can do is you can also add the voltages that you've just calculated earlier, the voltage for R1, the voltage for R2, and the voltage for R3. Do these 3 voltages add up to something close to 5? Okay, because remember, this is a voltage divider. Series circuits divide voltage. So series circuits are supposed to divide part of that 5 volts across R1, part of that across R2, and part of that across R3. And if you add up the voltages of each of the 3, we should have the total voltage that's verified by voltmeter number 1. Now, voltmeter number 2 is very interesting. Voltmeter number 2 has its positive lead, or the red lead of the voltmeter, attached to the top of R3, top of R2, the 330 ohm resistor. The bottom of voltmeter number 2 is attached to ground. So guess what? This meter is attached across 2 resistors to ground. As the notation says, VM number 2 is across 2 resistors to ground. What do you think that voltage would be? Think. What would that voltage be? It's across 2 resistors to ground. Does it make sense that it would be the sum of the voltage across R2 plus the sum of the voltage across R3? Write down your prediction. We'll verify with the calculation in a moment. And then finally, voltmeter number 3, where it's positioned, is directly across resistor number 3. So it should verify as being the calculated value of the voltage across R3, which we calculated 1.43 volts a moment ago. So VM1, you would suppose, okay, we should have 5 volts. VM2 should be the sum total of voltage across number 2 and the voltage across number 3, and voltmeter number 3 is across 1 resistor. It should be the 1.43 volts. Okay, so let's go ahead and do this on the breadboard to verify the numbers. And what we're going to do is we will measure the resistances, we will measure the individual voltages and voltage total, then we'll measure the voltages of each of the voltmeters to ground. Now, why are we doing this? why we're doing this is these voltmeter measurements, number 1, number 2, and number 3, are very similar to the type of testing you'll do in the field. In the field, you won't be measuring across components as often as you will be from test points to ground. You'll simply attach the black lead to some reference ground point on your circuit board, and with only one hand, one probe, touch different test points of interest and confirm that to a known set of values to see if everything is matching. If it doesn't match, then that will indicate where you might have a potential source of an error or some sort of a problem that could be on the board, could be some damage. So this kind of exercise of knowing ahead of time what each of these voltmeters should read in comparison to what they will read is very important to your troubleshooting in the field. So what I'm going to do now is switch off of here, go back to camera mode. Okay, so back to camera mode, remove the formulas, bring the circuit board back, remove the calculator, bring this guy here so that we have these in similar focal points. I'm going to raise this a little bit to here so we can see this better. And then turn on the multimeter to measure. First thing we wanted to do was measure resistance, which we did earlier. Well, actually, let's go ahead and confirm. So when we go to start our measurements, you want to do the continuity test. When we touch these two leads together, this should go to 0, and I should on this meter see a green light light up, and you may or may not hear the beeping tone through the microphone of the camera, but it beeped. So first thing you do is that. Next, you want to double check the resistance measurements. And as I've said before, you cannot measure the resistances on the board if there's any connection to the power supply. So I can remove the connection to the power supply by breaking the circuit open at the LED. The LED is there only to show us, yes, we have a complete circuit. Pull that out. And then now we don't have any solid connection between all 3 resistors to the board. I can measure each one of these separately. The first one's supposed to be 220 ohms. I will go ahead and take my probe, put one probe here, put the other probe here, and hold down steady, and I've got 220, which is great. And then hold here and here. I should get something close to 330, and hold steady, hold steady. Try not to block the camera. Oops, probe's in the wrong place. There we go. Hold steady. Something close to 330 ohms, and yes, I get 332.5. Does it matter with the resistor which lead is on what side of the probe? Right now I have the red lead on top, black lead on the bottom. I'm going to switch this around. Again, this is more review for you, because we should be comfortable with understanding this by now. Measuring resistance is not polarized. So when I go to hook up here, now I have the black lead on top, red lead on the bottom, and I still get 332.5. All right, last resistor should be a 220. We want to measure that this is a 220 and confirm, hold steady, 220.9. If it's jittery, it changes, you can go ahead and no, we should illuminate to see things a little more clearly. You can press hold if these numbers are dancing around. They generally won't for resistance if you've got the probes on nice and steady. All right, so we don't need the hold here as much as we did for the other kinds of measurements. Now, we want to measure the voltages. Now, to measure the voltages, what we need to do is to put our jumper back in place of the LED, so the jumper goes back in there. And now that the jumper's in place, we can turn on our power supply. Power supply is on, and we want to switch this to DC volts. It's measuring DC in the voltage scale. And I set my probes across the first resistor, and we predicted something close to 1.43. Let's see where this ends up. Let me untangle my leads here for a moment. Untangle, untangle, untangle. And here we go. Let's go ahead and measure. 1 lead across the top, 1 lead across the bottom. Hold steady. Do I have something close to 1.43? Yeah, pretty darn close, 1.45. And since the third resistor is the same ohms as the first resistor. R3 is the same ohms. This is 220 and that's 220. Shouldn't the voltage of this be very similar to the voltage here? Shouldn't we get something as a 1.4 something across the last resistor? Let's go ahead and check. Make sure I'm on the wire. Okay, there I am. Oops, messed up. Jammed it, sorry. Rebuild it. Pressing too hard. And here, hold steady. And here, hold steady. And see what it is that we have. Unless I've pulled something off the board that I should not have, it should show me the voltage. Oh, silly me. Let's go ahead and hook this up properly. And hook this up properly. And this is a good troubleshooting sequence. I'm not measuring the voltage I should be measuring. So that tells me a couple of things. Either one of the leads is now, because I smashed this onto the board a moment ago, this lead may not be all the way down. If I push this all the way down, and push this all the way down, do I have the voltage I want? Ooh, this is a good troubleshooting sequence. Why don't I get my 143? So double check up here. I get my 143. This was 2 something. 2 point, yeah, as this is jumping around, what you're going to need to do here is wait for a steady moment, press the hold button, and record it. Is this close to your calculated value? As you previously calculated, let's take a look. You previously calculated around 2.14, and yes, it does measure 2.18. So the first calculation of 1.43 volts, we had a voltage measuring very close to that. Second calculation, about 2.14, we have a 2.18 volts. 2.18 volts, and let me come back here. Oops. Get back here. And now let's go ahead and make a measurement across the third resistor and see what's going on there. Why I'm not measuring anything, because if I'm measuring voltage across first resistor, second resistor, I must have current flowing through here. And so let's see what's going on with the third resistor. Maybe I'm not connecting this properly. Let's go here. Oops, take off the hold. All right, I'm expecting something close to 1.43. Let's go ahead and measure. Oh, okay. That's the answer. I get, oops. Hold steady. Lock. And I expected something close to 1.43, and I get 1.448. Pretty darn close. I'm happy with that measurement. Why we weren't getting something before? This resistor on this end may have been slightly up off the blue rail. It's supposed to be just a tiny bit off, like this, raised, so that if I needed to use a mini hook, I can grab the leads with my mini hook. But as I was pushing down earlier and I flipped the board, I may have crumpled it and it may have lifted this off the board. So now we verified the individual voltages. Let's go ahead and measure the total voltage. So take off this. Let's go ahead and do this. Now tell me if this is going to be a problem. I'm going to put black lead on top, red lead on the bottom. Am I getting close to my 5 volts? I sure am. I've got 5.12 volts, but it's measuring negative. Am I going to freak out? No, not at all. Negative 5 volts just simply means I need to be mindful of where I'm putting my probes. So I'm going to flip the leads around. Red probe should be on the more positive side of the circuit, which is on the red rail. And the black probe should be on the more negative side of the circuit, which is the blue rail. And if I use the correct polarity of the probes on the board for measuring voltage, I should get a nice positive, in this case, 5.15, 5.14 volts. Okay, all right. Now the voltages at specific points, voltmeter number 1, voltmeter number 2. So voltmeter number 1 was connected across the first resistor all the way down to ground. And it should be the same as voltmeter number 4, total voltage. Voltmeter number 2, so I'm going to leave the ground here. In fact, what I'm going to do is what we typically do in the field, and that is we leave a permanent connection to ground. So I'm going to change the lead for just a moment. And this will be the one-hand technique. So I'm going to use a hook. Oops, come back here. And use the hook. All right, there. All right, so now the black is hooked to ground. All I have to do with one hand, as I've said, is touch test point number one, which is voltmeter number one, which is at the top of the circuit. So I go to touch, bend the resistor here, touch right here. I expect 5, I get 5. If I go to the second test point, which is across the second resistor to ground, it'll be the voltage across 2 resistors. So it should be the sum of the 1.43 plus our calculated 2.14. And if you haven't done that math, it should calculate to be 3.57 volts. Now let's go ahead and make the measurement. Leave that at ground. This is a one hand. See, I've got one hand here to press hold. It's ready to jitter. The other hand is only holding the red probe. The black lead is permanently hooked to ground, which I'm using a mini hook to do. So let's go ahead and touch test point number one again. One hand. Test point number two, one hand. And is that close to our 3 point? It's jittering around. Come on, hold steady, hold steady. 3.57, we saw 3.5 there for a moment. So 3.48, not bad. If I release this, press and hold. Yeah. Okay. 3.3, not as close to 3.57 as we would have liked, but again, there's some resistances on the board, maybe some contamination, certainly some tolerances to the resistors. Are we somewhat close to the 3.57 volts? And let's go ahead and do this one here. Put this down, and it will land on it eventually. All right, so 3.599 is almost 3.6, pretty close to 3.57. All right, so let's go ahead and do the last one here. We expect 1.43, and we have 1.43. Okay, so with one probe, test point 2, test point 3, you can see how fast and easy this is in the field. Not to have to use both hands to hold probes. You simply lock the black probe onto ground somehow. And you could do this with an alligator, or you could do this with a mini hook. Once that's locked on ground, then you just simply go the individual test points. TP1, test point 1, test point 2. If I'm on the metal, it helps if I'm actually touching metal. And then test point 3, like so. All right, that confirms your voltages across each of the resistors, also confirms the voltage divider, and now you should have been able to fill in your table. Okay, so your numbers should look very, very similar to these numbers here. The calculated value of 5, what did you have a measurement? 5.11, 5.12. Your calculated total ohms, 770. I think I measured 771. VR1, you calculated 1.43 volts. We measured 1.41 to 1.42. So each of these voltages that you've calculated should be very close to the measurements that you measured. Are your measurements close? They don't have to be exact, but are they close? Yep. When you measure the voltages across each of the resistors, are your measurements close? They don't have to be accurate. They don't have to be exact, but they're close. The answer is yep. And how about the voltages across voltmeter 1, 2, and 3? Are they reasonably close to our predictions of 5, 3.57, 1.43 volts? Yep. All right, that takes us, actually concludes the solution for voltage analysis number 1, the voltage divider challenge that are presented back in topic 5. So the solution is given to you for the 3 resistors of the 220 in series with the 330, in series with another 220 ohm resistor. And now we'll go to the second task, and the second task was a design task. So if we take a look at the next task, what it is that we have for you to do, this is again from topic number 5. This was, suppose You need to design. You are the designer now. You need to predict ahead of time what you think is going to happen. Uh, this schematic specifies that the source is 5 volts. You want a 30 milliamp current to flow. You need to determine what value of resistance you need to pop in here in order to flow 30 milliamps, because the design specs require 30 milliamps of flow with a 5-volt source. So what do? You go back to Ohm's law, and when you go back to Ohm's law, you recall that you put your thumb over the R, and as you put your thumb over the R, take a look at what's left in the formula. You have a V over an I. So what that means is resistance would be calculated as voltage over current. Do we have a voltage? Yes, that's 5 volts. Do we have a current? Yes, that's 30 milliamps. Can you calculate what that ohms ought to be? Well, let's go ahead and take a moment and do this. Right here. Okay, so following Ohm's law, V divided by I. So we take the voltage and we're going to divide by the desired current. So on our calculators, we will simply take 5 and we're going to divide by 30 milli. And on this calculator would be 30. And milli is this button, second function right above the 5. And so I will hit Shift 5, and I should see the little milli come up on display. So there's my 30 milli, and then I will hit equals, and then I get an E. What do I get? 166.67 ohms is our desired ohms. So again, how do I do this if I don't have the prefix calculator? If I don't have the prefix calculator, turn this guy on, and it would be 5 divided by, and I key in 30 milli by doing this, 30. And remember, milli, according to and I showed you this before from Professor Al-Hamal, he put together the engineering prefix chart, and milli is 10 power negative 3. If you don't already have this recorded into your journal, you need to do so from a previous training video that I've done. You'll find this very, very helpful. So anyway, so 10 power negative 3. Well, you have a 10 power key right here. 10 power key is 10x, and then it is negative 3. So you do not hit the subtract function. Subtract is not negative. There is a negative key right here. This is negative in parentheses. So you're just going to touch this, and it shows negative, and you hit 3. So 10 power negative 3. That's how you key milli into this type of calculator. And then you hit equals, and lo and behold, you end up with some scientific value, which is useless because, again, any 10 power over here that is not a multiple of 3 is scientific notation. So we want to hit our engineering key. So we touch engineering, and voila, we end up with 166.67 ohms, which is the same result as what we had previously calculated here. Now, if you wanted to practice not using the prefixes on this calculator, you can do so. So let me hit clear, and we simply take 5 divided by 30. And how do I key in milli if I'm not going to use the prefix? I'm going to use the EXP key. And as I said before, the EXP key is the same as the 10x key on other calculators at the bottom. In fact, they're pretty much in the same place on the Casios. And so I will hit the EXP. And when I do the EXP, it'll show E, and I need to show this as negative 3. So negative is this key here. You do not hit this. That's the subtract function. This is not negative. Negative is this negative symbol shown in parentheses. So I will go ahead, key this guy in. Now I have 30 exponent negative 3. Now that is 30 milli using the 10x or / exponent key. And if I hit equals, boom, this automatically shifts to the proper decimal place location. So 166.67. But it's a whole lot easier not having to use the 10x or exponent key with this calculator. Just simply take 5, divide by 30, second, M right there, boom, you're set. It's that much faster. And that's why I recommended this particular Casio calculator for you. All right, next, now that we have the ohms, how are you going to set up your resistances to get 166.67 ohms? Wow, you've got 100 ohm resistors. You have less than 100, you have 10 ohm resistors. So I suppose you could put 100 plus six 10 ohm resistors or seven 10 ohm resistors, and you'll get close to 170 ohms. So with 170 ohms with a bunch of resistors in series, yes, you could achieve this amount of ohms in order to achieve the desired current of 30 milliamps. We'll enter a new device called a potentiometer, something that we can dial in, a variable resistor that we can tune to be very close to this number in order for us to achieve 30 milliamps. Now, let me show you how that's done. Okay, so now that you're on my share screen, again, we reiterate the schematic. R is unknown until we just calculated 166.67 ohms. It would be tedious to build a bunch of series resistors in order to achieve 166.67. The best thing to do is to use a resistor that can be dialed in to something close to 166.67 ohms in order to achieve this current. What the circuit looks like, my friends, was hidden in the previous challenge question, as I put a piece of white paper over this. I've got some kind of circuitry underneath this, and I'm measuring current, and it's showing you that this is now, the digital multimeter is now set up as an ammeter because it's measuring current. So my ammeter presently is set to the milliamp scale, and on the milliamp scale, DC milliamps, it's showing milliamps on the display of the multimeter, and I'm getting 30.02 milliamps. So how is this going to be achieved? Yes, we could put in a bunch of resistors, but I said, let's go ahead and use a pot. And that was something for you to explore, do some internet searches. What is a pot? What is a pot? Not what is pot. So what is a noun for something singular as opposed to the more popular use of pot. So let's talk about pot as an electronic component. And what it looks like here, my friends, is I'm going to remove the cover and you'll see in a moment, ta-da, I've shown and this is the potentiometer you have in your kit. It is a blue box-shaped device with a knob that can be turned by hand, or you can put a slotted screwdriver in here to rotate this knob. And if it's hooked up properly in the circuit, and I'll show you in a moment how to do this on your breadboards, you can dial in the amount of resistance that is specific to the amount of current that you're looking for. So what I have is and I'm going to, and I did change this a moment. This needs to be back on the red rail, which it will be in a moment. So it should be current flowing between the negative rail up to here to row 14 to here into one of the legs of the pot. The pot has three legs. I've got three other kinds of pots shown here. I've got a manual finger turning pot. This is a 200 ohm pot. Somewhere on the pot's body should be a marking as to what the maximum ohms of this pot can be tuned to. And this particular one here sits flat on your board. It's got three leads, and I'll explain what the three leads do in a moment and which of the three leads we're actually going to connect. This here is a very special pot. This is a precision pot. This is a 15, between 10, 12 to 15 turn pot. So this gives you, instead of a single turn, a single rotation, such as what's on this black one here and the blue one here, these are single turn. Instead of a single turn to rotate from one extreme to the other of resistance, this one takes 10, 12, 15 turns, depending upon the manufacturer. And as it takes more turns to reach from 0 ohms to total ohms. In this case, this is a 20 k ohm pot, 20 kilo ohm pot. We can dial this very, very carefully with a few turns in order to get very close to the desired value. Here's another example of a potentiometer. This one goes to show again the characteristic 3 prongs. And this one happens to be a 5 kilo ohm pot, meaning this is going to be the amount of ohms from one end of the scale to the other extreme. All right. So what we're going to do is to show you more images of pots in a moment and in detail how to use them and how to connect them. So let's go here. Actually, to clarify, this connection to the blue rail is not a mistake. What it is that we happen to have is a connection that is not connected to the voltage source. So we will have, and I'll redo this so that you can see the measurements in a moment. And let's go ahead and do this to here. Yeah, so the illustration was actually correct. I just needed to remove the power supply. If I have the power supply in place, the mere connection of the power supply will change things. And I don't want to release the whole. This will change from the 121, but I don't want to do that. Let's just go ahead, remove the power supply. That way the blue rail here has no continuity with this blue rail. And all that we're measuring is the ohms by virtue of the following. I've got 1 ohm meter lead on a jumper to this blue rail, to this jumper, to the center pin of the potentiometer, and one of the side pins of the potentiometer is pulled out here to this blue rail, so the other ohm meter lead is set up here. So what I'm measuring right now is this is set on ohm meter mode, showing me ohms and showing me 121.3 ohms for this potentiometer. The potentiometer, and I'll show you in another slide in greater detail, but let me just show you the underside of the potentiometer. The underside of the potentiometer shows 3 pins, and the connection for variable resistance is between the middle pin and any of the outside pins, either one of the outside pins. And so what I've got is the jumper wire, brown jumper wire to the center pin, and on one of these outside pins is a connection of this other jumper wire, so that I'm only using the center and one outside pin for dialing the amount of resistance that we need. Once this is on the board, all we need to do is just rotate this little, rotate by hand. The little arrow will tell you what position it's in right now. It looks like it's about 11 o'clock. I can rotate this to about 9 o'clock. I can rotate this down to 6 o'clock. I can rotate this over to, say, 4 o'clock. So as I rotate this around, the amount of resistance will change between the center pin and one of my outside pins, which is what I have here. So what I have is I've dialed this in right now to 121 ohms. We really need 166. 0.6 ohms. And with this particular style of potentiometer, it's a little tricky, and I'll explain why in a moment. Some of these are what we call linear pots, meaning it gives me a very consistent from one end to the other end of the potentiometer range. And let's see, these guys are rated at, let's see, what's it say here? It looks like it's a 1 k ohm pot. Yeah, 1 k ohm pot. 103 is the code for 1 k ohm. It looks like, no, excuse me, a 10 k ohm pot. Anyway, what it is we have here is they could be a linear pot, meaning the change from one end to the other end of the pot is consistent, or it could be a tapered pot, which means that it is not consistent from one end to the other. One part of a rotation is not the same as the other part of the rotation on the other end. Anyway, let me just show you what it is that we have here and how challenging it is with the single turn pot, how to get 167 ohms. So what we're going to do is right now, this is set at 121, but just by touching this, rotating just, take off the hold. Taking off the hold, I'm down to 3.5 ohms. I'm pretty close to one extreme of the pot. So let me go ahead, rotate, I'm down to the minimum 1.6 ohms. Now let me rotate the other direction, try to increase this. Increase. Okay, now I've got about 61 ohms. And if I rotate ever so more carefully, oh, I've got it up to 151. And with a whole lot of patience and a whole lot of very careful tuning, I might be able to get this up to something close to 160. Yeah, see, just a tiny bit of a turn gets me past. So you just really have to be very patient. And that's as close as, for the amount of time that I'm going to give this, as close to the 166.67 ohms as I'm going to get. Once I get this dialed in to this amount of ohms, then when I go to hook this circuit back up and measure the current, I will have something that's pretty close to my 130, excuse me, close to my 30 milliamps. Okay, so I've reconnected a couple of things. The orange jumper wire is now positioned up one so that it is now connected to the red rail. Red rail brings us down to this particular row 24. Row 24 connects with this brown jumper wire to the center pin of the pot, and one of the outside pins of the pot to here. I broke the circuit open. This orange jumper was previously connected to the blue rail. I've removed part of it so that it is now hanging up, and then the other part of the ammeter is hooked up down here. So I've created an open between this point, and I'm measuring between the open. And with ammeters, you do have to be mindful of the polarity. I've got the red lead on the more positive side of the circuit, and I've got the black lead on the more negative side of the circuit. And with this dialed in at 163 ohms instead of the 166.67, I was hoping to get 30 milliamps. This is getting a 31.8 milliamps. And I got that locked on hold here, all right? So just to show you how sensitive this pot is, the moment I take it off of the hold, this number will probably jitter for a number of factors. Let's take a look and see how it changes. 31.28, okay, 31.29, 28, 27, 26. So we're close to the 30 milliamps. We're not spot on, but at some point in time, as close as it seems stable, you put the hold on, you record the reading, and you're done. Now, I'm going to readjust the pot, see if I can trim this as closer to 30. And I'll tell you, with this particular pot, we're not going to be able to get the degree of precision I'm hoping for, but let's give it a shot, because in the previous photo, I was able to get it down to 30.0 some kind of digit. Let's see, release the hold, and now come over to the pot. And what I'm going to use is rather than my big hammy fingers, I'm going to use a screwdriver, and with a handy dandy screwdriver, let me hold the board. And just touching the board changed the current slightly. All right, come over with my potentiometer screwdriver, and ooh, I got it. Ooh, ooh, ooh. Let go, let go, let go. 32. Oh, I'll had it there for a moment. Let go. I'm making just ever so slight nudges. And that just goes to show how sensitive this particular pot happens to be at this particular ohmic range. Ooh, 29.72. That's pretty good. That's actually closer to the 30 milliamps than we had a moment earlier. So 29.84 milliamps, pretty darn close. And this will be closer to the 167.67, 166.67 ohms that we wanted. Now, in greater detail, let me show you the flip side of pots and exactly how we are able to change the resistance of these devices to get them to be tuned to a specific amount of ohms to satisfy required circuit conditions. And remember, the circuit conditions for this exercise was for you to design some kind of circuit, some kind of ohms between a 5-volt supply trying to achieve 30 milliamps. You did the calculation using Ohm's law. You discovered, yes, you're going to need 166.67 ohms. You could have built that amount of resistance with a bunch of separate resistors, but that would have been tedious, and you would have come close. But a faster way of doing things is with a potentiometer. So let's go ahead and show you in greater detail how potentiometers work. Okay, so as you're looking at my slide, it says, what is a pot? Pot is a potentiometer. What is a pot? A potentiometer has 3 leads, and two outside leads and one middle lead. And so what to do with a pot is it is a variable resistor, meaning it's a type of resistor that will allow the resistance to change. So in this particular slide, I'm showing the ohm meter connected to each of the outside posts of the pot. So here's the pot on the left, and it shows red hooked up on one of the outside ones. The middle one's not connected. The other outside one has the black mini hook, and it doesn't matter. Red goes to whichever side, and the same with black, because you know resistance has no polarity. But what is specific is that these mini hooks have to be hooked to the outside pins. So what this demonstrates is as I'm hooking up my mini hooks of my ohm meter to the outside pins, this shows a maximum amount of ohms that this particular potentiometer is designed to be. And in this particular case, it's a little bit over 9 kilo ohms. What I wanted to show here is in this illustration on the left, the pot has a knob that is attached to the face of the pot. The knob is this little chrome-plated insert with a black melamine body. And the position right now is approximately 7 o'clock in its ability to rotate. So let's think about this as a volume knob on your radio. Well, I've turned the volume knob all the way down to minimum. And what I've got here is, in this particular case, at this extreme, maximum ohms. But if I rotate this all the way to the other side, which is what I have here, to the other extreme, it shows, hey, I still have the same amount of ohms. It makes no difference where this knob is rotated in the grand scheme of this connection. Is as I'm rotating the knob left, right, or anywhere in between, the amount of ohms on the outside pins do not change. Okay, they will not change until I do a different connection, and that different connection is going to be moving one of my connectors to the middle pin and leaving the other connector to one of the outside pins. Makes no difference which of the outside, but one in the middle pin post, one on the outside post, and let's see what happens with the next sequence of images. Okay, so right here I've got 3 images, and what I'm showing is I happen to have the red mini hook to the center pin, center post, if you will, and I've got the black to one of the outside pins, outside post, and I have the knob turned all the way over to the right. And as it's turned all the way over to the right, I'm getting an ohmic reading pretty close to what I had previously as an extreme. So I've got 9.44 kilo ohms. Now, as I slowly rotate this knob from its maximum position, or 5 o'clock, if you will, rotate to 12 o'clock, which is what I have here, it looks like I've got approximately half of the 9 volts, half of the, 9.44 kilo ohms, about half of the amount of ohms shown in this particular display by rotating the knob, in this particular case, a left turn counterclockwise. And if I continue rotating, still leaving the hooks as we did, the red in the middle and then the black on one of the outside pins. As I rotate to the other extreme, it goes to show my ohms going all the way down to a minimum. And in this case, it could go less than 1 ohm, but I happen to have this dialed in at 1.2 ohms. So as you can see, there's quite a bit of difference between 1.2 versus 9,440. Okay, so I can adjust with this particular potentiometer, since it's rated out to a maximum of 9 kilo ohms, anywhere from 1 ohm to 4 point something kilo ohms, all the way gradually by rotating this knob slowly up to its maximum of 9.44 K ohms. Very, very interesting. So let me show you by switching to the camera in a moment how we do this on the physical pot itself. And let's do that. Okay, so this is a better demonstration of the physical pot itself. This is very similar to the 3-pin one you have in your breadboard, but since it's physically larger, it allows me to make this demonstration a little more visual, easier to understand. So potentiometers have 3 connecting posts. 1, 2, 3. One in the middle and 2 on the outside. And this is what it looks like from the control side, meaning here's a shaft that I can rotate clockwise or counterclockwise, and my connecting posts are one in the middle and one on either side. This is showing us the pot without a convenience of a knob. So if I were to try to turn this with my fingers, it's a little slippery. It's because there's not much to grab a hold on. So if I go to physically attach a knob, and it's very easy to do with a set screw and set the knob in place, this allows me to be able to hold the potentiometer with one hand and rotate gradually the shaft, which rotates the amount of ohms inside the pot from some extreme to the other extreme, okay? And let's go ahead and make a connection to the posts with my ohm meter. So I'm going to connect the middle post. Well, let's go ahead and connect the outside post first. So I'm going to connect one to this outside and connect the other one to this outside post. Okay, so on the outside posts, any rotation of the pot should not give me any appreciable change of the amount of ohms. So let me move this over here where you can see this and see this here. Okay, all right. The multimeter is set on reading resistance, as you see, and I'm showing scale of 2 kilo ohms, 9.34 shows here, and I have the knob all the way over, in this case, on the left. So as I rotate this clockwise from one extreme to the other, this is my 9.34, and rotate from one extreme to the other. Let it stabilize for a moment, 9.34. So what this goes to prove is the outside pins are not affected by the position of the knob. The knob only changes the amount of resistance inside of this device to whatever you hook up to the middle pin. So watch what happens here. If I hook this up to the middle pin, like so, okay. I'm hooked up to the middle pin and it shows, okay, I've got 9.34 kilo ohms. However, between the middle pin and the outside pin, as the knob is in this position, I will rotate halfway. So here's 12, roughly 12 o'clock. And what do I get? Something about half the amount of ohms. 4.77 kilo ohms. Rotate a little further, you can see a decrease to 3.811 kilo ohms. Rotate a little further, and it'll decrease to what you see, and rotate further, and rotate all the way. And this goes down to, and make sure that's as extreme as possible. For this particular pot, doesn't go to 0, but it does go to 1.3 ohms. So you look at this, you say, well, you know, KOGUY, this seems counterintuitive, or might seem counterintuitive. If I rotate this knob the same way that I'm accustomed to rotating a knob on a stereo amplifier, or the knobs that you have on a television set, or your radio, car radio, the older car radios before digital, you rotated knobs. Trust me, ask your mom and dad. So it seems if we rotate all the way clockwise, we should get a maximum. And if we rotate all the way to counterclockwise, we should see a minimum. Why is it backwards? Well, it's not backwards. It just means that this particular knob in its rotation happens to be measured between these two posts. If I want this to rotate clockwise in an increasing fashion, all I have to do is switch from my mini hook from this outside post to this outside post. I'm going to keep the red where it is on the center post, but now I'm going to switch the outside post connection to go from here to here. Okay, so now I'm on the outside post, and voila, check this out. The knob is at our traditional minimum if this were a volume control. And then if I were to rotate this in a clockwise fashion, you can see I'm increasing the amount of kilo ohms. increasing to about halfway, and increasing until I reach all the way over, and I will reach the maximum of our 9.34 or 9.35 kilo ohms. So now we have a rotation that is consistent with increasing the amount of ohms. And all that we've done here is use the center and this outside pin versus the center and the left outside pin. All right. So when you go to use this potentiometer in your breadboards or in your projects, if you were to make a connection between one of the inside pins and one of the outside pins, and you rotate your knob in a counterclockwise fashion to what is traditionally a minimum, and it shows a maximum, whereas you rotate all the way over to the far right-hand side and it shows a minimum, all you have to do is to switch your connection from one outside pin to the other outside pin. Same thing holds true for your breadboard potentiometer. Same thing is true for this, okay? So all we have to do is just switch one of our outside pin wires, and now the rotation is consistent with increasing and decreasing the ohms. So as we rotate traditionally to the left, we would expect a lowering of volume, lowering of brightness, in this case, lowering of resistance. And if we rotate clockwise, we can see that increase gradually, increase more as the knob continues all the way over to the other extreme. Voila. So this is how your potentiometer works on the outside pins and from one middle pin to one of the outside pins. So now I'm going to move all this over and show you a variety of different potentiometers that you might encounter. Turn this off. Remember, always turn your machine off when you're not using it to save the batteries. All right, I've got a slew of different kinds of potentiometers here. And the ones that are shown on the breadboard that are above the channel, these are breadboard potentiometers that are single turn, and they come in different physical configurations. I can turn this pot right here. This is the pot you have in your kit. I can turn this with my fingers. I can rotate like so, or I can bring a screwdriver down and rotate it with my screwdriver. This particular one happens to have a shaft, and it allows me to rotate by my hand or rotate with a screwdriver. This particular one is really nice. It's flat on the board and it shows right quite visibly the amount of ohms from maximum to that it's capable of. It has a really nice large knob that's flat. Again, I can use my fingers or I can use a screwdriver. The rest of these use screwdrivers. So this one here, this one here. So the physical size of the pot doesn't indicate the amount of ohms. The amount of ohms is determined by what happens inside the pot. And then the last two pots that I have here in the single turn, this one adjusts from the front and this one adjusts with a set screw on the top. Now, the more interesting ones that you will encounter, and if you ask your electronics instructor in your lab to pull these out, you can see that these are rather elongated. Again, they, like all pots, have 3 pins. It's your 3 pins, 3 pins, 3 pins right there, 3 pins right there, another 3 pins. And they are marked 1 ohm, 5 ohm, 10 ohm, 20 ohm, 50 ohms. So the amount of resistance on the extremes is shown properly marked on all the pots. What's unique about these are multi-turn pots. So if this were a 10 ohm pot and this were a 10 ohm pot, one rotation would take me from one extreme to the other, okay? Here, I would take 15, no, anywhere between 10, 12 to 15 turns of that knob at the end of the potentiometer's a little knob. If I put this standing up, maybe you can see right there. There is a screw post, and the screw post can be adjusted. Let it focus there for a moment. It's focusing on the other part of the board, sorry. Anyway, there is a screw post, trust me. And if I bring a screwdriver in here, I rotate this, I can get 15 turns of anywhere between 10, 12, and 15 turns of pot rotation in order to get from one extreme to another. So what does that mean to you? What that means is with a multi-turn pot, you will be able to get more precise and gradual adjustments of your resistance between the middle pin and one of the outside pins. Okay. Remember, like that larger pot I showed you a moment ago, the outside pins don't change resistance. The outside pins show you the maximum resistance of the pot. The variability, the changeability of resistance only occurs between the middle pin and one of the outside pins. Either this middle pin and this outside pin will reflect a change when I turn the knob, or this middle pin and this outside pin will reflect a change, depending upon where I rotate the knob. So how do you decide which to rotate? And that all depends on your breadboard. So on your breadboard, we happen to have the single turn pot here. If I were to use this particular pot, this one here, this multi-turn, I probably would not use this one facing in this direction. Why? Because my screwdriver has to come from this side, and I happen to have some hardware like this power supply that's in the way of my screwdriver. So if I wanted a 5K ohm pot and I wanted this specific pot, I would rotate this way. Okay, insert it in the board, and that way my screwdriver would come from this side, do the turning in my screwdriver shaft, and the handle would not encumber any type of interference from something like the structure of the power supply. So how would I wire this? Well, let me go ahead and use the 1K ohm pot. So the 1K ohm pot, if you look at this carefully, I happen to have a slightly different pin spacing than the pot that's on your board, the pot that came with your kit. The pot that came with your kit, let me see if I can set it right there. You can see there's my middle pin and one of my outside pins, and these are separated by about 2 rows. Between here and here is possibly 3 rows. So let me see if I line this up. Will it line up with my jumper wires as I have set up on the board? No. This would line up with this jumper wire. This one clearly will not. So I have to create a larger gap on my breadboard in order for these jumper wires to make contact with these 2 pins of the potentiometer. That's easy to do. So let me go ahead and redo this for just a moment. Very easy. Just go ahead, grab this guy up, grab this guy, move this over one. Now I created a 2-row separation, and the 2-row separation allows, and let's see if I bring this down, does that match? Look very carefully. Does that match here? Does one pin match up with this jumper wire, and does the other pin match up with this jumper wire? So all I have to do to put this on the board is to make sure this first pin, this left pin, is somewhere on row 25, and this middle pin is somewhere on row 23. So I very carefully look on the board and find a convenient place for this to slip down into. So is my outside pin on row 25? Is my middle pin on row 23? It is. Line it up carefully, push down like so. And now this is on the board and making continuity with the rest of the circuitry. So what I'm going to do is reinsert my jumper wires. We're dialing this in and show you how this guy's dialed in. So just get my jumper wires back out. I'll set this up just a moment and put this on pause. And okay, so I've got my ohm meter connected to one side of the pot with my red mini hook to the very first pin. My black mini hook is connected to blue rail, which is connected to the middle pin. So now I'm going to use the screwdriver and make an adjustment on the post. Right now, the ohm meter happens to show I've got 71.6. Now, when you use a screwdriver to make any adjustment on the board, I highly recommend you hold your component down and then bring your tool to the adjustment post, and let's take a look here, get it in there and rotate. I'm going in the opposite direction. If I rotate in this direction, you can see I'm going down. If I rotate in this direction away from me, I am increasing. So let's go ahead and get this in here. So rotate to increase. And I want to get this up to, hold on. And gently go back to rotate. As you can see, I get some really nice gradual changes, far more gradual than what can be achieved with a single turn pot. And by using a multi-turn pot, I can dial in the amount of ohms to a precise value far more easily than otherwise. So look at this. We wanted 166.67. 166.67. That's pretty close to 166.67. 167 is a lot closer than what I would get with the breadboard pot that came in the kit. You can get it with the breadboard pot that came in your kit. You just have to be a whole lot more patient in making those adjustments. And see right here, there's my 166 point. It was bouncing at 166.67 a moment ago. If I let it stabilize and just play with this just a tiny bit, there's my 166.7 right there. Isn't that slick? So that's how you would use a multi-turn pot to get more precise variable resistance tuned into the amount of ohms that are necessary in order to achieve the amount of current that you are looking to design your circuit to. So as you can see, I've wired the circuit to create an open at the bottom of the circuit to measure current. So this orange wire was previously connected directly to the blue rail. So I've broken that open, detached it, and then made a connection here. So my open is between this point and this point to which I attach one ammeter lead and the other ammeter lead, and my current is showing 31 point something milliamps. So very close to the desired amount of ideal 30 milliamps based on my desired 166.67 resistance of ohms. So if I go to right now, while this is live on the board, see if I can tweak this just a little bit. Let's see, which way do I want to tweak this? We'll find out in a moment, because one way I will increase current, the other way I will decrease current. And let's see, well, that increases it. So let's go the other way. Dial it, dial it, dial it, dial it, dial it. Ooh, went past it. But anyway, as you can see, if I'm patient with this and tweak this ever so gently, I can get a whole lot closer to my 30 milliamps, as was the design parameter. And that's achieved with a multi-turn pot for greater precision in adjusting the ohms to produce the desired current that we were looking for. All right, that completes the answers for troubleshooting question number 2 from lesson 5. Let's go on and take a look at the challenge questions that were posted for you in topic number 6 video. All right, our topic 6 troubleshooting question number 1 was, if you recall from topic 6, we were playing with parallel circuits, and we had 3 resistors in parallel as shown in this illustration, and I'm using the ohm meter to measure across the bank of resistors. Remember, the nickname for a set of parallel resistors is called a bank, and the nickname for a series circuit is called a string. So as we look at this, the 3 resistors from the previous calculation of three resistors of the values in parallel worked out to be 57.2 ohms. Now, if you don't recall or didn't watch video number 6, the resistances are for number 1, 100 ohms. For number 2, 220 ohms. Number 3, 330 ohms. So 100 ohms in parallel with 220 in parallel with 330. The total ohms in a parallel circuit do not add. They do not summate as they would in a series circuit. In a parallel circuit, the value of your total ohms will always, say it again, always, and write that in your journal, always be less than the lowest ohmic branch. So if the first one was 100 ohms, second one was a 220, and the third one was a 330 ohms, your total ohms has to be less than 100 ohms. And in this particular case, we calculated 57.2, and in this case, we measured 57.2. But here's the challenge, the troubleshooting. Suppose, I mean, in an ideal world, the calculated value at 57.2 ohms, your R2 measures at 57.2 ohms like mine does, but suppose it doesn't. What if your R total on the measurement is not even close to the calculated 57.2 ohms? What could be a problem? What would be some scenarios that would cause you not to be able to measure 57.2 ohms? Suppose you measure some other kind of ohms, like 100 ohms, you measure 220, suppose you measure 500 ohms. What are some of the possibilities? You needed to, from the previous topic 6, write this down in your journal. You needed to copy this down. If you haven't done so, copy this down now and leave some space in your journal for you to noodle this out for a moment. Think about what possibilities could occur. Might there be a miswiring? Might there be the selection of the wrong ohms? You think you pulled out 100 ohms. Maybe you didn't pull out a 100 ohm resistor. Maybe you accidentally pulled out something other than the 100 ohm. They all look pretty similar. And if you haven't learned how to read your resistor color codes yet, then I highly, highly suggest that you do take a moment and go back to learning how to read your resistor color codes. And in reading your resistor color codes, here is the chart that I had presented in a previous training video. This is from my colleague, Professor Nabil Al-Hamal, and he created these charts on really, really nice little plasticized cards. And it goes to show Ohm's law formulas, it goes to show resistor color coding, and it goes to show your engineering prefixes, the powers of 10 associated with what words are the prefixes, what are the symbols for the words, what do they represent in English terms, trillion, billion, million, thousandth, millionth, and then the decimal equivalents shown here, and then also the symbols that are used for the different properties and the units that are used for the symbols. Voltage is V, current is I, resistance is R, whereas the volt symbol for volt is V, symbol for ampere, which is a unit of current, is an A symbol for resistance is R, but the unit of resistance is ohms. And what's the symbol for ohms? Omega. So this is very handy information that in previous training videos I've asked you to transfer into your journal, and that would be helpful for us in this exercise. So yes, we could not measure 57.2 ohms, possibly if one of these was incorrectly pulled out. So if you're not sure on how to read the resistor color codes, you can always rely on your multimeter to make sure these are in fact 100, then 220, then 330 ohms. What else would be possible? If, let's say, you measured the three resistors and they were as you wanted, 100 ohm, a 220, and a 330 ohm resistor. They are the right ones. And you put them on the board and you still don't measure 57. What else could be wrong? Yes, we did talk about some kind of miswiring, but let's have you do this exercise. We wanted to have you calculate R1 parallel with R2. The symbol here with the double verticals is a parallel symbol. So R1 parallel to R2, what are those ohms? R1 parallel to R3. What are those two ohms? What are those ohms? R2 parallel to R3. What are those ohms? What this is suggesting is perhaps one of the resistors is either defective, one of the resistors could have been burnt out, one of the resistors is not connected properly. So if one of the resistors is not connected properly, very likely you're going to measure some number that you've calculated here, okay? So let's go ahead and try some of these calculations. Now remember, your task is to put this stuff in your journal. So as you write down this question set into your journal, I'm going to go ahead and pause this recording and we will go to a camera view and show you a review of how to do these calculations. So here's your three resistors in parallel. We start off with the 100 ohm resistor, the 220 ohm resistor, the 330 ohm resistor. And if you look closely, yes, all three resistors are connected at the top to the red rail. Then they come down to some row, which is connected to a jumper, to some other row down here connected to another jumper to the blue rail. And each one of these resistors is connected similarly, so that, remember, the definition of parallel is these resistors are in parallel. And there was a very, very specific way of saying this. There was an if and only if statement. Two things have to be satisfied. What are those two things? Well, first of all, the leads on one side of these resistors have to be connected to a similar point. And look at the upper leads. They are all connected to the red rail, so they are all connected to a same point. But the second condition that has to be satisfied is, are the lower leads connected to a separate same point? So this lower lead is connected through this jumper to the blue rail. This lower lead of this resistor is connected through a set of jumpers to the blue rail. And this lower lead of the resistor is also connected through a set of jumpers to the blue rail. Yes, so all lower leads are connected to the same point down here. That makes these electrically in parallel with each other. So we hope to measure, and I'll bring in the multimeter, and here we go. Set this to read omega. And again, never ever hurts to double check your continuity. So you take your two, yes, it beeps, it goes to 0. You might hear the tone. All right. May or may not hear the tone. The microphone may have a challenge at that frequency. So now we'll go to omega. And in the omega setting, in the ohm setting, you can see we've got megohms here, and I'm just going to connect this to the jumper wire that I conveniently left on my breadboard, and then go ahead and connect this one up here. And come on, make the connection, let it stabilize. And am I close to my 57.2 calculated? Yes. I'm showing 57.2. We're going to review the calculation here in a moment. So let's go ahead and turn this guy off, make the disconnection, set this aside, bring in the calculator. And we bring in the calculator, turn the calculator on. And we said, let me bring this camera up just a touch so we can see the calculator a little better. All right. So we said we had 100 ohm calculators on. So we have 100 and it's in parallel with 220. So how did we calculate the reciprocals? It was calculated as 100, and I have my reciprocal key, reciprocal plus 220 reciprocal plus 330 reciprocal equals, hit the reciprocal key one more time, and then equals, and what does our calculator show? Shows us 56.9. Let me see if I did that correctly. Might not have hit the right number. So 100 reciprocal plus 220 reciprocal plus 330 reciprocal. Ah, okay. How easily we can push the wrong button. 100 reciprocal plus 220 reciprocal plus 330 reciprocal equals, then reciprocal, then equals. All right, so we calculate 56.9, pretty close to our 57.2, or measured 57.2. Your task was to calculate R1 parallel with R2. Your task was to calculate the 100 ohm parallel with the 220. All right, the 100 ohm parallel with the 220. And if you hadn't seen the topic 6 video, let me just reiterate a slide with you. So I present this slide from our topic 6 video, the one preceding the one we're on right now, as a reminder of how to calculate total resistance of parallel circuits. And it's called the reciprocal formula. So RT is shown in the upper left-hand corner as being equal to this giant fraction. You have 1 over 3 different reciprocals. So you have 1 over the sum of the reciprocal of R1, reciprocal of R2, reciprocal of R3 right here. And the formula itself may look intimidating, but it's actually quite easy on your calculator. And as a review point, some calculators have reciprocal buttons designated these one of 2 ways in the middle left. It could be an X-1 key. It could be 1 over X key. Both of these are called the reciprocal key on your calculator, and they both achieve the same task. So if we were to calculate the R total for resistors in parallel, and let's say I have in this sample, the R1 is 220, back up, dyslexic me, sorry. R1 is 20 ohms, R2 is 40 ohms, R3 is 30 ohms. You wanted to calculate the total of these. You're not adding them straight up. 20, 40, 60, 60 plus 30 is 90. No, it's not 90 ohms in parallel. If they were in series, it would be 90 ohms. But in parallel, we said that the total ohms have to calculate to be less than the lowest ohmic branch. So something less than 20 in this case. So the keystroke sequence is shown here. 20, which is the first ohmic value, you hit reciprocal, then add the second ohmic value, you hit reciprocal, then add the third ohmic value, hit reciprocal, hit your equal key, hit reciprocal, hit equals, and in this case, you generate 9.23 ohms. So try the sequence on your calculator, verify that you're able to calculate 9.23 for the first example, and then verify that you can calculate 216.51 ohms in the second example using my keystroke sequence as shown. This was shown in great detail with keystroke steps on the camera in live view in topic number 6. So if you didn't see that, please review topic number 6, and you can see all of these buttons calculated in real time on your calculator. All right, so that being said, let's go ahead and do the calculations for this particular, let me go to here and go to previous. So here's the previous, and then I relabeled this and also redid this slide so it provides a little better greater clarity. It shows the circuit built, and it shows that I've measured 57.2. The actual calculation works out to be 56.9 ohms. For R1 of 100 ohms, R2 is 220 ohms, and R3 at 330 ohms. So I thought that the schematic alongside with the regular circuit build would be handy to keep the numbers in view as we go through these calculations. So your first task, if R3 somehow was defective or something in that branch was defective, leaving only R1 and R2, what would you measure for the total ohms? That was your task. You needed to calculate R1 and 2 in parallel with each other in the absence of R3. R3 is gone, let's say, for whatever reason. Here in the second calculation, you are asked to calculate R1 parallel with R3. So R1 is here in parallel with R3. That meant something has happened with R2 such that it electronically is no longer part of the circuit. So if it isn't, for whatever reason, bad wire, blown resistor, something, misconnection, and only R1 was parallel with R3, what would be those ohms? You should know this. No, you should be able to calculate this, and we'll do this together in a moment. Then you want to calculate R2 parallel with R3, and then that will generate a number. And if your measurement is not close to 56.9 ohms, which is the calculation of all three in parallel, 57.2 is reasonably close to 56.9. I'm happy with this, given the margin of error for your resistors and the wiring, the ohms of the wires on the board. That's pretty okay. But suppose it's something really whacked, totally different, and is one of these three, then that would lead you to your conclusion. So let me go ahead, switch back to camera mode, and we will go ahead and solve these using our calculator. All right, so now let's go back. We are now onto the calculator, and your task, you copied this into your journal so you know what the task is, should already be written in your journal. You were tasked to calculate R1 parallel with R2. R1 is 100 ohms, so clear 100, hit your reciprocal button, add 220, 220, hit your reciprocal button, hit equals, reciprocal equals, and I calculate 68.75 ohms. Write that down for your first calculation. Write that value into your journal. Now, don't write my value down. Write what your display of the calculator shows. And if you follow the same keystroke sequences I did on my calculator, your calculator should show this number. So this is not a watch and see, this is a watch and do exercise. You're hands-on. And if you like this style of hands-on training, you like this the aspect of you doing with the learning, then hit a like on the YouTube and perhaps even subscribe so that next time we have new videos that pop up, you'll be informed when another video pops up, because my next one is going to be on series, next two will be on series parallel. So anyway, back to this. You should write this down, record this into your journal, and the next calculation is R1 parallel with R3. So let's clear. R1 was 100 ohms, so 100 reciprocal, and we're going to add that to R3, which is 330 ohms. Hit the reciprocal. There's no add after this because there's only two resistors. So you hit equals, you hit reciprocal one more time and hit equals, and you calculate 76.74 ohms. Record that. Now, yes, it shows a bunch of other digits as giblets after the decimal point, but we always round to two digits after the decimal point. So 76.74 ohms is what you would calculate for R1 parallel with R3. Now, the third calculation you were asked to make was R2 parallel to R3. So that would be a 220 ohm resistor reciprocal in parallel with 330 ohm reciprocal equals reciprocal equals, and you calculate 132 ohms. Okay. So these values you should calculate. Like I say, don't just watch me and see, watch me and do. You do these same keystroke sequences. Put the video, YouTube on pause, and make sure you do the calculations as I've shown you. Then you write down the values as you have generated on your calculator, and let's see if they jive with the actual solution. So let me go ahead and go back to share, and the solution set should be presented here. Voila, look at that. Calculated 68.75, that is the solution for these two. Calculated 76.74, that is the solution for these R1 parallel with R3. You calculated R2, the third calculation of 132 ohms as being the parallel relationship between R2 and R3. In each one of these, is the 68.75 less than the smallest ohmic value? Is the 76.74 less than the smallest ohmic value? You look at the 132 and you say, some of you may already have caught this, some of you may not. You say, hey, I calculated an R total here that's 132. Isn't that higher than my 100 ohms? Is there a mistake? No, there is not. In the initial world, where all three resistors were connected properly and calculated properly, the ohms calculated to 56.9 ohms, which is certainly less than the lowest ohmic value. We calculated 132, not for all three resistors in parallel. Keep in mind, I said in this scenario for item D, suppose something happened with R1. R1 either burned out or the circuit path was incorrectly wired and it's no longer part of the circuit. You only have R2 parallel with R3. Well, take a look at the schematic. The schematic shows 220 parallel with 330. Aha. These two are the only two resistances that we're calculating for a total in this case. And is 132 ohms, in fact, less than the lower of these two branches, which is 220 ohms? Remember, the 100 is not part of this calculation. So yes, although you calculate 132 and 132 is higher than the original R total for all three resistors, this scenario of troubleshooting only is interested in R2 parallel with R3, and just with two resistors in parallel with each other, these specific two, 132 ohms was calculated. Cool. So that was the first troubleshooting question. Now, the next one is more interesting because the next one takes us into some current considerations. Actually, before we go to do the next one, let me go ahead and verify some of these ohms with the live camera. So let me switch off of this, stop the share, go back to camera mode, and in camera mode, bring in the circuit. And let's go ahead and go to ohm meter function. And let's go to make a measurement. Now, remember, you've already recorded these numbers in your journal, so we're just verifying what would happen if these scenarios presented a fault condition. So the first fault condition was leaving R1 parallel with R2. That says that something happened to R3. So either R3 burned out or R3's path was wrong. So I've got this nice jumper here. I'm just going to conveniently yank it up for a moment. If I yank it up, won't it pull R3 out of the circuit? There will be no continuity between R3 to the red rail and R3 to the blue rail if I yank this jumper. And once I yank this jumper, all I have in parallel are these two resistors. And that's why the first calculation was R1 parallel with R2. You calculated 68.75. I calculated 68.75. Let's see if I yank this jumper. Do I get something close to 68.75? So hold this down so I don't take this all off the board. Yank, set this aside. Wow, that's pretty darn good. We calculated 68.75 and this measures 69.1. That's close enough for government work and close enough for us, given the tolerances of the resistors. Tolerance means margin of error and some of the stray ohms that are on the board by virtue of the wires. That's a really good measurement to your first calculated value. What's your second calculated value? Your second calculated value was to calculate R1 parallel with R3. First was R1 parallel with R2, presuming something was wrong with the third resistor. Now we're going to calculate R1 parallel with R3, presuming something's wrong with the second resistor. So what I'm going to do is I'm going to move this jumper over to here. I have to rebuild this. So R3 is back in the circuit, R1 is back in the circuit, but R2 is clearly not in the circuit. What did you calculate? What's your journal say? Your journal says, or should say, 76.74 ohms. And is this measurement pretty darn good, pretty darn close to 76.74 ohms, 77 again, given the tolerances of the resistors and some stray ohms that are on the board by virtue of the jumper wires. We're hanging we're dancing the happy dance. All right, the third scenario was R2 parallel with R3, presuming something was wrong with the first branch. Either the resistor burnt out or the wiring was wrong. I can very easily test this because I've done neat wiring on the board simply by moving one jumper, positioning this from here to here. Remember, if I have one fault condition, which is an open here, I have to rebuild the rest of the circuit. So do I now have R2 parallel with R3 only, and R1's no longer part of the circuit? What did we calculate for R2 parallel with R3? Your notes say 132 ohms. What do we measure, my friends? 132.5. This is hot stuff. We are all dancing the happy dance right now because our measurements are jiving with our calculations. You are knowing how to do your calculations. You're knowing how to use your calculator. You're knowing how to use your breadboard, how to make these measurements. And you should be doing this in real time, as I've done, by hitting the YouTube on pause and trying this out yourself and verifying those currents. Okay, so the first one was a fault condition for number 3. Yank this out. Yes, it's close to 68.75. The second condition was maybe something wrong with R2, so we will build this over here. R2 is out, so you only have R1 parallel with R3. We calculated 76.74 ohms. We measure 77, pretty darn good. And the last consideration is maybe something was wrong with the first resistor path. So we yank this guy out, put this over here. And very quickly, we were able to determine R2 parallel with R3, with R1 being faulted out for whatever reason. In this case, I've removed it from the circuit by virtue of removing the jumper. We calculate 132, which jives with our calculated value. Hot stuff. Hopefully, you've just done this. Put this back, and do we achieve our original 57.2 ohms? We do indeed. All right, so now we can go on to the next challenge. And let me go back to share screen. And on the share screen, we happen to have our next challenge. And the next challenge is shown as question number 2 from topic number 6, troubleshooting. It says, compare your answers below to the solutions discussed at the end of topic 7, training. I'm going to reword this, but what it asks you, suppose your IT doesn't calculate close to the calculated current of 87.87 milliamps. The ideal ohms is 56.9. And if we use 56.9, we should be able to calculate that into 5 volts to generate a certain amount of current. So your task, and you write these calculation tasks down if you haven't already from the previous video, your task is to calculate current for R1 and R2 only, meaning R3 is dead and gone. Then you recalculate the current for R1 parallel with R3, meaning R2 branch is defective and gone, so there's only these two left. You already calculated the ohms. Based on those ohms, what would the current be? And then you want to calculate the current for R2 and 3 being in parallel, R1 being defective or burnt out or misconnected, okay? So let's record this information and do the calculations and see where we end up in our calculations. All right, so if we review a reworking of the slides, so it's a little cleaner, and what I've done, as I've done previously, is bring in the schematic. So the schematic shows R1 as 100 ohms, R2 is 220 ohms, R3 is 330 ohms. It's built that way in the illustration. And so you were asked to calculate the currents, because when you go to measure current, the current's supposed to be something close to 87.87 milliamps, but for some reason it's not. So if it's measuring something other than 87.87 milliamps, it could be one of the previous fault conditions we discussed a moment ago, and that is one of these branches could be defective. One of these branches could be miswired, leaving only 2 branches intact. And so a possible scenario is given as, we've discussed before, one of these are defective, and so that leaves you 2 remaining. And so in the previous calculation, you did calculate R1 parallel with R2, and that calculated to be a specific amount of ohms. You recorded that. And so when you're calculating the current based on those ohms, you're calculating 5 volts based on the amount of ohms for R1 parallel with R2. So R1 parallel to R2 only was previously, let's go to here, previously 68.75 ohms. All right. So with your calculator, take your 5 volts and divide 5 volts by 68.75. You do that very easily. And what does your calculator show you? Write that value down, and we're going to determine if that matches with your solutions shown here in a moment. The second scenario here presumes in item C. Suppose something happened to R2. R2 is burnt out, missing, not hooked up, whatever, leaving you only R1 parallel with R3. So with only two resistors in parallel with each other, the ohms worked out to be 76.74 ohms. So your calculation of current is calculated as 5 divided by 76.74. You should be doing that right along with me. 5 divided by 76.74, and you hit enter, and you should have a current, some kind of milliamps. Okay, you might see a 10 power negative 3 on your calculator. If you see a 10 power negative 2 or 10 power negative 1, hit the engineering key, and it'll get you at least into engineering. So with any other kind of scientific calculator, it should show you some kind of milliamps, meaning some kind of number, and 10 power negative 3. On the preferred calculator, it'll show you some number with a engineering prefix, the lowercase m for milli in the upper right-hand corner. All right, one more calculation to do, and that is 132 ohms would result as your total resistance if only R2 was left in parallel with R3. This presumes something was wrong with the first branch. So you end up with two resistors in parallel totaling here 132 ohms. So if you take 5 on your calculator right now, divide by 132. So 5 divided by 132, hit equals. You will have a third amount of milliamps, some third number, 10 power negative 3, or some third power with a lowercase m in your calculator display. Now, let us go ahead and confirm what you've calculated. All right, we will go ahead and do the calculations. I'm going to stop the share. Stopping the share, we'll go to real time on the camera and real time on the camera. Let's go ahead and see what we've got. We will do clear, oops, clear, clear, clear. And it was, let me get to bring this guy back up. All right, and minimize and minimize. Okay, so I'm back onto the calculator display. So 5 divided by the first ohmic sequence, 68.75. There, 5 divided by 68.75, and then you hit equals. And it does show you, in fact, 72.73 is how you'd round this off, 72.73 milliamps. Now, in the absence of the prefix calculator, if you were to use a other calculator, turn this guy on, would be 5 divided by, 5 divided by 68.75. You hit equals. And if you get some scientific notation that ends in a power less, that's not a multiple of 3, this power is -2, so that's not going to work for us. You hit the engineering key. When you hit the engineering key, it shifts it to the appropriate 10 power -3 or -6 or whatever it should be. And this tells you have 72.73, remember the third digit rounds the second digit, 72.73 milliamps. And again, if you don't recall why 10 power -3 is a milli, you need to go back to the previous chart that I showed you that shows 10 power -3 is in fact milli, which is a lowercase m on our little card. And it shows as 7273 with a lowercase m. All right, let's go ahead and do the second calculation. And the second calculation was clear. We're going to take our 5 volts and divide by the 76.74 ohms. So double check that I've entered it correctly. So I have 5 divided by 76.74 and hit equals. And this one gives me 65.16. This is how I will round this off, 65.16 milliamps. Write that down. Hopefully you've got the same number. Or again, in your other calculator, you take your 5, divide by 76.74. And again, 10 power negative 2 is not engineering, so you hit your ENG key, and it shows you 65.16, 10 power negative 3, which is your milli, okay? So having the preferred calculator saves you a few extra steps. All right, the last calculation is going to be your 5 divided by 132 ohms. And 5 divided by 132 ohms brings you to 37.88. You'd round that to 0.88, so 37.88 milliamps. Hopefully your calculation jives with this. And again, if you're not using the prefix style calculator with the standard calculator, 5 divided by 132, I'm sorry, that's clear so you can see the display. 5 divided by 132. Okay, and then now I'm going to hit the equals, and I get some power other than some multiple of 3, so I do have to hit the engineering key, and it is, as we've done on the other calculator, 37.88 milli. 10 power negative 3 is a milli, so 37.88 milliamps. And on the prefix calculator, we'll call this, it does show as a milli, so 37.88 milli. So you've recorded all of those numbers, and as you've recorded all of those numbers, let's go ahead and see how this works with our solutions. So let me go ahead and share screen. Now, keep in mind, before I share the screen, you have written everything down, you've done the calculations. Boom, there is the solution, or there are the solutions. 72.73 milliamps, 65.16 milliamps, 37.88 milliamps. That answers the questions for certain fault conditions in your troubleshooting. So if you measure any of these currents, it would show that, yeah, for sure, we have a problem with one of the resistors, okay? And so what we're going to do, well, let's finish answering the questions. So answer for E, you've already done previously. What can you conclude if RT is not the calculated 56.9 ohms? Well, clearly, one or more of the resistors is either burnt out or misconnected. Therefore, our total is not 56.9. So any one resistor falling out of the circuit for whatever reason, misconnected, would give us some different value of ohms, which we had calculated previously in the other slide. Now, F, what can you conclude about why IT is not the calculated 87.87? If it's any one of these 3, it verifies the fault conditions that we had supposed was in place. So let me show you. We're going to stop the share and go to camera mode. Stop share. Where's my stop share button? Come on, mouse. Stop share. Okay, back to camera. So on the camera, here we go. Where's my circuit? It's here. Okay, where's my meter? It's here. Let's go ahead, put this into the ammeter mode. Do not make the connections yet. I'm going to raise this up where we can see this a little more clearly. Turn on the illuminator, and I'm going to switch from hooks to pin probes, because this gives me a very precise momentary connection, which I only want a momentary connection, like so. All right, and so I need to break the circuit open, and I'm going to break the circuit open. Yeah, I have to rebuild this so that I can break the circuit open. So give me a moment with a parallel circuit. I do need to do some slight readjustments here. Okay, guys and gals, here we go. Moment of truth. Multimeter is set in the ammeter mode, specifically to measure milliamps. It's DC, and the circuit is rebuilt such that I still maintain my parallel relationship with all three resistors. All three resistors are connected at the top to the red rail. All three resistors are connected to the orange line right here, the first resistor to the second, second to the third, and leaving only one path here to go to the negative rail, all right? So what I'm going to do is, in order for me to measure total current, I'm going to have to create an open right here between where the yellow wire connects to where it connects to the two orange wires connected together on row 19. That will create an open, and from this open, I should be able to measure my original 87.87 milliamps. So I'm going to show you how we're going to do that. I'm going to very carefully just raise this up and stick this off the board somewhere, doesn't matter where, just leave it open like that. Or I can, yeah, it's fine. I can actually take it off the board like so. All right, so now I have an open. The open that I've created is where the yellow wire was connected. The yellow wire was previously connected to where these two orange wires were together and then connected to the negative rail. So I created an open between here and here. So with my probes, and only at these connecting points, I put the red probe on the positive side of the open, which is on this side. I don't put it where the wire was because there's no electrical connection I can make with the orange wires. I have to touch one of the orange wires right here. Remember, just putting your wire in an empty socket does not make continuity underneath the board to the set of tie points that are consistent. So that is the positive side of the open. And then the negative side of the open is, of course, ground. So we're hoping to see something close to 87.87 milliamps. And lo and behold, guess what? I got 87.8 milliamps. That's hovering between 87.8, 87.9, rising slightly. We've got some heat action going on, but is that close to 87.87? Yeah, pretty darn good. All right, so total current is measured there. And I will continue to measure total current by creating a fault condition by lifting these jumpers. And again, the neat circuit building allows me to very quickly make these measurements. And very quickly, the first fault condition was something occurred in this path for the R3 where it's either burnt out, miswired, whatever the case. I can replicate that fault condition simply by removing this jumper and setting it aside somewhere else. I now have an open. This R3 is no longer part of the circuit. I only have R1 parallel with R2. Therefore, the current that I calculated earlier for R1 parallel to R2 is only for these two in parallel with each other. We calculated 72.73 milliamps. That's what you should have recorded in your journals. Let's go ahead and make the measurement from here to here, and let's see how close we come. We wanted 72.73. We got 73.2. That's pretty darn good. All right, we're definitely in the ballpark. All right, the next fault condition was saying something happened to the second branch, so I very easily moved this from here to here, meaning I have to reconnect the third branch to be parallel with the first branch. So the third branch, R3, is in parallel with the first branch, giving me an open to measure for current. And we predicted 65.16 milliamps. Let's go ahead and make the measurement from here to here. Is that close to 65.16? Not bad at all. We got 65.8 milliamps. We're dancing the happy dance so far. Now go ahead and create the fault condition on resistor number 1, branch 1, by moving this jumper here. So we now have two branches that are intact. R2 is in parallel with R3 with one circuit path to ground, and this is where we're going to measure the currents from here to here. Notice R1 is disconnected, is no longer part of the three original parallel resistors. What did we calculate? 37.88 milliamps. Let's see if we get close to 37.88. Lo and behold, 38.80 something. Close enough for government work. We are spot on. So that's how easy it is to measure total current and each of the branch currents for a fault condition if you subscribe to the neat circuit building method that I've been promoting all along. And that is your resistors cut, bent, and using jumper wires in a fashion that is easy for you to follow. So by rebuilding the jumper wire, do I still have the original 87.87 milliamps or something darn close to it? Yeah, there's my 87.0, pretty close to my 87.87 milliamps. Happy camper. We are dancing the happy dance. So let's go finally reiterate back to our share screen and share. All right. So do we in fact have let's see, am I sharing the right screen? Yes, I am. So do we in fact verify measurement close to this calculated number, a measurement close to this, measurement close to this, and our I total under ideal conditions is pretty close to 87.87 milliamps. So E, what can you conclude why RT is not close to the calculated 56.9 ohms? There's a fault with one of the branches or more of the branches. Second question, what can you conclude why IT is not the calculated 87.87 milliamps? You just did it. You just did it by assuming some kind of fault condition in one of these branches, resulting in only two resistors at a time being connected together, and then only these possible scenarios for current that could happen if I only had one fault condition per branch. Pretty exciting indeed. You all and we should be dancing the happy dance. All right, so we've reached the end of this training video. So let's reiterate what it is we've been able to accomplish, and that is we were able to solve the two questions that were presented to you, the circuit troubleshooting questions in topic 5, and the two troubleshooting questions in topic 6. And you learned a lot about potentiometers, learned about more about hooking up your ammeter, and hopefully, like I say, occasionally we may get so excited about building our circuits and making our connections on the board, we might accidentally burn a fuse. It can happen. It's happened to me. And so it can happen. So you should have spare fuses just in case, because we're going to be measuring a whole lot more currents with circuits coming up. So what's coming up? This concludes topic 7. Topic number next training video will be the first of 2 parts on series parallel circuits. Series parallel circuits are a combination of circuits where part of the circuit's in series, part of the circuit's in parallel. We'll get into those discussions in the next training video. So if you enjoyed the hands-on approach, if you enjoyed working along with me with your calculator, working along with me with your breadboard and building the circuits and verifying your calculations with measurements and learning the troubleshooting, definitely hit the like button, definitely hit the subscribe button. Doesn't cost you anything for either one of those. And if you want to support the channel by clicking on Patreon, yes, you can definitely help to support the channel. It allows me to be able to continue making more of these videos. And so with that, I thank you very much for your kind attention and look forward to seeing you on the next topic video, topic number 8, which will be the first of 2 parts on series parallel circuits. So with that, my friends, adios, adieu, auf Wiedersehen, aloha. Stop the share and stop the